Analysis of dual-tone multi-frequency tones in a pre-recorded sound file with a continuous wavelet transform approach by Gabriel Ramos and Gabriel Torres.
Hello, I'm with the group of Gabriel Ramos and Gabriel Torres. I'm Gabriel Ramos, and I'll be running you through our code of phone tone. The general idea of this code is to take a recording of phone keys being pressed and determine through an analysis what keys have been pressed. The analysis we chose to utilize is a continuous wavelet transform uh, with a complex Morlet wavelet provided to us by our professor, Dr. Luis Montejo. Uh, First, we begin by adding a path to where the file may have been saved. This would not need to be done if the file is saved already in the MATLAB folder, but we have it elsewhere. Then we use audio read to extract the sampling frequency and the points of data of the signal. WAV read may also be used, but only in older versions. Then we transform our points of data into a row vector because they are given to us by audio read as a column vector. And we determine how long the signal was with the time step, and we generate a time vector. This plot is to help us visualize the waveform so as to see the spikes in which the keys were pressed if there is not too much background noise. Our wavelet parameters were a complex Morlet. Through testing, we used a central frequency of 1 Hz and a bandwidth parameter of 1000. For the frequencies that we will be passing through, we chose only the ones that are unique to the phone tones because it would save us a lot of computational time, as if we had done it over a wide range, we would still only reduce ourselves to these eventually, and we would have wasted time and processing power. And then the scale factor, which allows us to run the CWT. The C is a matrix of complex coefficients, which we then uh, transform from having complex coefficients with imaginary numbers into just with normal numbers by getting the absolute value. Afterwards, we identify the maximum point and we divide the entire matrix by that maximum point so as to normalize it so that we may pass a tolerance based on percentage. Then to help us visualize this step, we plot the CWT in 3D, and we also plotted top-down view so as to only see the peaks. The tolerances we recommend are 30% at each frequency, assuming there is not too much noise. Otherwise, we would have to play around with these numbers. And then it is simply a matter of using a nested loop to turn anything under the tolerance into 0 and anything over the tolerance into a 1. After this, we also plot this response to help us visualize where there is sound still coming from and what has been reduced to 0. At this point, assuming there isn't any disruption from noise, we have a for loop with many if statements inside of it, which essentially work by seeing if the sum at any given column throughout the matrix is equal to 2, which would indicate that there are two frequencies currently playing, thus meaning that there is a tone there, which we can identify. And then we check if the sum of the next point would not be 2 anymore. It essentially means that the tone has been completely pressed, and then we can look at the point right before it to identify which frequencies were present, so as to, with every specific pair, determine what key was being pressed. And as that happens, we also have a counter that adds +1 to itself every time it finds a different key. You can see that with each different pair, we can identify a different key. And finally, we display the amount of digits that were in the signal by just displaying the number of the counter reached, and then we display what was actually pressed with our W vector, which has saved each individual press, so it also shows them in order. Thank you very much. I will now leave you with Gabriel Torres.
Hi, my name is Gabriel Torres, and I will be discussing how to interpret the output given by the MATLAB script. Now, I will play an audio file that contains the sound of all keys being pressed in consecutive order. Such order is 1, 2, 3, 4, 5, 6, 7, 8, 9, asterisk 0 hashtag. This file contains all the possible dual tone multi-frequencies that will be used. This was recorded with a computer and a smartphone. This is the visual representation of the sound file where we obtain the amplitude through time. It provides a quick perspective on the noise level and the time where each key was pressed. On this recording, there is a bit of noise and talking in the background. Next, we plot the CWT in 3D. This gives us information on the amplitude of the specific frequencies used in the dual tone multi-frequency system. In this case, the frequencies being studied have a high response with little noise interference. Probably, the most important visual representation is the top-down view of the CWT. Here, you can clearly see which dual tone multi-frequencies go together and the time in which they happen. Some noise is represented as faint light blue vertical lines. The tolerances will ignore them if they are below the threshold. This next diagram shows the CWT converted into a binary system. The ones are in red, while the zeros are in blue. Also, all the noise has been removed. This is the point in the script where the values of each column are summed. When the script detects two red squares in a column, a total sum of 2, the program looks for the symbol appropriate to the dual tone multi-frequencies recorded at that instant. This is a 3D view of the binary CWT. It doesn't provide much information, but it represents some information not provided in the top-down view. For example, the width in the frequency axis of each peak. This can be critical for cases with higher noise levels. Here, I want to focus on three things. The first one, the tolerances are kept the same as the recommended ones. These aren't output, but they're good to show. Then, as output data, we have the amount of digits and the dial interpretation. The number of digits is 12, and these are 1, 2, 3, 4, 5, 6, 7, 8, 9, asterisk, 0 hashtag. Now, we will discuss a real-life example. In this case, we have an fcase.wav file we are going to hear. This is a fast dialing of a phone recording. So now we will add a path to MATLAB. So we use the standard procedure where we add path and then we insert the file name. Right now we will remain with the standard tolerances, and we're going to run the program. So first off, it says that the amount of digits is 8, and this is the interpreted number. We have the first figure. This is the amplitude file. We have then the 3D version of the CWT. Then we have this, and this is really important. Here we can count more or less the amount of digits that we used. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 12 and it says 8. Perhaps there are some that are missing. When we return to the binary type, we see that some are missing in the top. This may be due to the tolerances. If we lower the tolerances of the higher section, let's say from 3 we go to 1, we should have a different result. Now it says that we have 12 digits and the numbers are all there. If we look again at the binary up-down view of the CWT, you can see that now a few red bars here have appeared. Even though some of the red lines in this frequency range look a bit thin, maybe if we lower the tolerances for the 1336 Hertz part, we can check for any error that might possibly happen. So these are the numbers, and we will repeat it once again just to make sure it's the same result. So yes, we have the same number of digits and the correct response for each digit. So it was a successful dial interpretation.